everybody. Today we will be talking about graphs and how to work with graphs, how to calculate the number of connected components, and etc. So we will start with the first. So we have what the graph is. Graph is a set of vertices, kind of points, and edges, where each edge consists of two vertices, and that there is an edge between u and v. So for example, here is the graph. 1, 2, 3, 4, 5. Okay, here is the graph, and v is the number of the vertices. So 1, 2, 3, 4, 5, and the edges are 1, 2, 2, 3, 3, 4, 4, 1, and 3, 5. Okay, this is the set of edges. However, the graphs can be of two types typically. So they're directed graph and undirected graph. What is the difference between two graphs is that in undirected graphs it looks like that. So there is, you can go from the vertex 1 to vertex 4 and from vertex 4 to vertex 1 back. However, in the directed graph, so for example, let us take the same graph. 1, 2, 3, 4, 5. And for example, this one is the directed graph where you can go from 1 to 2, but you cannot go from 2 to 1. So you can only follow their edges. So for example, it can be possible to be like that way. So there is an edge from 1 to 4 and from 4 to 1. So it's simpler to draw like this, but in reality it is something like that. So there are two different edges from 1 to 4 and from 4 to 1. And you can think of a directed graph as undirected graph as a directed graph, but where each edge has two directions, like this 1 to 4 and 4 to 1. What are the typical problems that we are going to solve on graphs? We first want to solve the problems of the connectivity, where you are given a graph, something like that, and you want to count the number of connected components. What I mean connected? Vertex U is connected to vertex V if there is a path between them. So what is path? Path is the set of edges that we should follow. So like kind of here from U to V, we can get taken this edge and then this edge. So because of that, they are in the same connected component. And for example, here we have three connected components in this graph. So this connected component, this one, and this one. Also, there are very interesting versions of typically undirected graphs. So there are three. Tree is an undirected graph that has no cycles, which is connected and has no cycles. So, for example, this is the tree, and this is the tree, like that. This is the tree. When each node, when you can hang the tree by the node, and it is known that it has exactly at most 2 children, then this will be binary tree. We are already familiar with that from binary search trees, so this is kind of the same vibe here. About this tree we don't know anything about, and there is a chain, another chain, or bamboo in the Russian literature. Is that each vertex has kind of one outgoing edge downwards. Okay. So about directed graphs, there can be rooted tree. It is the tree, it's simply the tree, but when all the edges are going downwards, they have a direction. Okay? And there is an acyclic graph, directed acyclic graph. Is the directed graph that has no cycles. For example, this one, it has no cycles, while when we think it of the undirected graph, where each edge, it has a cycle like that. But in this case, what is the cycle, right? We talked about the path. What is the cycle? The cycle is the path that starts in one vertex and ends at the same vertex. We talked a little bit about this on Hamiltonian path and Hamiltonian cycle, but right now we are giving this in more details. Okay, so the interesting question. So we have a connected graph on m vertices and m edges. Can you give me the lower bound, the connected graph? Can you give me the lower bound on the number of edges? Yeah.
I guess it should be sum. Yes, I think sum minus 1.
Sum minus 1? What sum? We have n and m.
So is it n and m? Is it connected graph?
Yeah, it is connected graph. Yeah.
I mean, n is the number of
vertices and m is the number of edges. This is the typical naming for for the vertices and edges.
Okay, so
can you tell me how many edges in the tree?
Exactly n, one for each vertex.
Not exactly, because as you can see, each vertex in this case has a parent.
Oh yeah, and minus
except
1.
for the one.
Yeah.
Yeah. Okay.
And minus 1.
So and kinda it doesn't have cycles, so like it's kinda their best graph possible in the sense of the number of edges. So if your graph is connected, then the number of edges in it is at least n minus 1. So if the graph is connected and the number of edges is n minus 1, then it is the tree. You could say that. So let us talk a little bit further about another thing, which is degree. Degree of the vertex is the number of adjacent edges. So for example, this vertex has the degree 4 because it has 4 neighbors. And in a cyclic graph there are 2 different versions, like there is in degree and out degree, typically written as DAG plus and DAG minus. What does it mean? In degree is the number of outgoing edges, and in degree is the number of incoming edges. For example, for this one it is 2, for this one it is 0. And out degree is the number of outgoing edges. So this one is 2, this one is 0, this one is 1, and this one is 1. Okay, so I think we defined everything that we need. And now we want to store the graph in some way in the memory. Typically, there are 3 versions on how to store a graph. We already talked briefly about that when we talked about Hamiltonian path. But still, I could try to do that from scratch. So there is adjacency matrix. And if there is an edge from V to U, you put 1 here. So it is the kind of Boolean matrix, either true or false, and which shows like simply, if there is a true in the row and column, then there is an edge from V to U. I think this is pretty clear how this works. Can you tell me if the graph is undirected, what matrix it would be?
It would be like some triangular matrix. Or so symmetric.
Yeah, it will be symmetric matrix. It will have like the triangular here and the same copied kind of like that. Because like if we will take the, it will be like that, right? So like V, U. Okay. Also sometimes there are like things in undirected graph there are no such problems, but in directed graph sometimes we could have very strange edges. We could have multi edges. This is where we have 2 edges from the same vertex, like for all three edges for the same. And loops is that there is an edge from the vertex to itself. So for the vertex to itself, in their adjacency matrix, it will be 1 at the diagonal. Okay, and there is adjacency list. Okay, sorry. What is the space complexity of adjacency matrix?
U squared.
Yeah, so it isn't squared. Wait. So adjacency list is a little bit more complicated. So this is their an array of lists where each cell stores a list. So for example, here 1, 2, 3, 4, 5, and it is simply shows their, like in their undirected graph, it doesn't matter, it shows the neighbors of each vertex, and in the directed graph it shows their outgoing edges. So for example, for this graph we have 1 and 2 neighbors, 4 and 2. They are not necessarily in their sorted order, so like they're kind of like, this is simply the neighbors. 2 is 1, 3. 3 is 2, 4. 4 is 1, 3. And 5 is 3. Oh, 3 is 2, 4, 5. So this is how you store, typically store their matrix. The main advantage of adjacency matrix is that you can check an edge in constant time. That's the main feature. If you want to check whether there is an edge from U to V, you just go there and ask in one. No fun. In the case of adjacency list, you could spend up to linear time if it is the full graph and the number of neighbors is linear. However, you can improve it to logarithmic time. What do you need for that?
Trees, I guess. But is it a linked list there?
Vector array list. Yeah, you could use the tree, or you can sort each list when you created a graph, and then you can answer in logarithmic time using binary search. Okay, so right now the question is how to find the number of connected components. So one kind of. So what we want to like, we started the vertex 1 and we kind of propagate, like visit all the vertices that are in that connected component. For that, there is an algorithm named depth-first search. the idea will be the following. So we will start from vertex 1, then we go to some neighbor, so vertex 4, then we go to some neighbor again to vertex 3, then we go to some neighbor 5 and mark all the edges, all the vertices that we visit. Then we see that 5 has no more neighbors because 3 was already visited. We draw back to 3 and then visit 2. So at each step we just visit one more vertex, one more possible vertex, and because we will go over all the vertices in the connected component, we will mark them all. So DFS is pretty simple. DFS of V, if was of V, then return, then set was V equals to true, and then go over all their edges. Sorry, VU DFS of U. So what we did here, we just, if we already visited this vertex, then do nothing. Then we said that we already visited this vertex, and then for each edge that is outgoing of V, we run DFS V. So how to implement this in two cases? So there is adjacency matrix and adjacency list. So in this case, it will be for U1n, if AV U, then DFS U. And in this case, it will be for U iterated through through the linked list of the graph, and just say DFS of U. So there are two versions. Either we can do with adjacency matrix like that. We should iterate over all their possible vertices and check whether there is an edge between them. And in this case, it's pretty simple. We just iterate over the linked list corresponding to this vertex. Okay. And that's it. How to calculate the number of connected components? We will write like was equals to false, and the number of components is 0 at the beginning. Then we iterate through all their vertices, and then if V was not there, if not was, C++ and DFS of I. So what does it mean? We iterate through all the vertices from 1 to n. So at first we take the vertex 1, visit all the vertices in that connected component, and then we iterate further until we found the vertex that is not yet in that connected component. Then we run again, and we already have 2 connected components, and so on. So this will calculate the number of connected components. Can you tell me their complexities in 2 cases? So there is the adjacency matrix and adjacency list. Can you come up with the complexity of these 2 algorithms?
Well, I think with adjacency matrix is the number of edges, I guess, total number of edges that we went through.
No. This is in adjacency list. Okay, so the thing here is the following. You see that we run this for only once for each vertex. Because if we are already here, like, and we go back here, we will return. So here, in this case, we iterate over each edge once. From vertex V to U, we iterate only once. But there are 2 problems. Like this one will iterate over all the neighbors. So it is exactly the number of edges because we iterate over each list only once. So in this case, it is all of them. And in the case of adjacency matrix,
it would be U squared?
Yeah, it will be n squared because the issue is that we do not visit we visit all the, for each edge, for each vertex we iterate n times to get all the outgoing edges. That is why you have n squared. Okay, good. Okay, so that is how we calculate the number of connected components. The very interesting thing here is that this DFS builds some spanning tree. What is spanning tree? Spanning tree is a subgraph of the graph, which is a tree, and connected subgraph, which is a tree. So, for example, here the tree can be like that. So in DFS, build your sum of the spanning tree. What does it mean? When you go from vertex V to vertex U here, and it is not visited, then we draw an edge between them, kind of in the spanning tree. So for example, here, what will be the spanning tree previously? We start with 1, we visit 4. So 1, 4 is the edge of our spanning tree. Then we go from 4 to 3. This will be the new edge in the spanning tree. Then we go from 3 to 5 and from 3 to 2. Please note that this edge we didn't take because when we go from 1 to 2, 2 was already visited. Like kind of when we roll back, 2 was already visited. Okay. Now we will talk about how to find any cycle in the graph. So we know if the number of edges is n minus 1, then it is 3, and the tree is a cyclic graph, it has no cycles. However, like we are right now working in undirected graphs. How to find the cycle in undirected graph? So suppose we have the spanning tree here. So obviously there are some edges that are inside this spanning tree and some of them are outside. So the question is, so suppose we take some vertex where the edge can go from this vertex. Can it go to this subtree?
Well, inside the spanning tree, I mean, it can go, but in the whole graph it can.
Yeah, in the whole, do you think that it is possible from here to here, an edge?
Well, I'm not sure I understand the question. So
the question, so we build a spanning tree, and then we want to understand how other edges will look like in this graph.
So
not in the spanning tree, yes.
Okay.
So this, like, is it possible for this vertex to have a neighbor here?
I guess yes. So
wrong. Let us think a little bit. Suppose we had an edge here. Suppose we had an edge here. If we have an edge here, this vertex, it cannot be in this subtree of the spanning.
How will everybody's heard about the bird?
У меня пара, перезвони позже. Okay. So how was our spanning tree built? So we get to this vertex, And then we go through all the neighbors.
Mm-hmm.
And then if we go to all the neighbors, we couldn't visit this already. It should be in this subtree. Because
Well,
it will go like that.
You mean if we started from the...
Yeah, we start from like
Okay.
kind of this is subtrees. These are like the first subtree, the second subtree, the third. So we
Okay.
went like that.
Yes. So yes,
Okay,
if
so
we
it
started
is-
from
it-
the top, it cannot be.
It is impossible, right?
Mhm.
Okay. Can it be to the right subtree?
It also can't, I guess.
Yeah, it also can because otherwise that vertex would be in that subtree.
Mhm.
Okay. So where their edges can go only?
Well, maybe inside or between the nodes or the leaf nodes.
Okay, so specifically, there are two ways of their possible of the edge. There is either the edge in its subtree to some of its children, like which are there, or to some parent. This edge is also possible. So then, how to find the cycle? The cycle is pretty simple. You just have to check whether you have an edge backwards. So kind of you iterate there, there, and there, and then you can have a cycle if there is an edge from here to some parent. Like this edge will be considered by this guy. It is the link to its parent. So we will find their cycle from that vertex. So another question. So suppose we have a directed graph. So again, we build this spanning tree. But it is becoming more interesting. So the first question, can there be an edge here?
No, I guess still not.
No, this one's still not, because otherwise this vertex will be in this subtree. Okay. Can we have this edge?
Well, also no, if it's like that.
Why not?
Well, if the arrows are directed that way.
No,
Or,
the-
no,
the-
no, no, okay. We
The
can,
arrow
we
is
can-
from,
we can,
yeah,
yes.
exactly. In this case we can, because like in their undirected case, it was visited from this node to there. In this case, it is visited from the right to the left, and there is no problem with that. And again, there are edges there and downwards. But this edge cannot create a cycle, because it goes from right to the left, and it cannot create the cycle. Because like if it creates the cycle, then the cycle is something like that, and then this vertex should be in this subtree, so it is impossible. Again, in the directed graph, the cycle also can exist only as they're going to some parent. So let us write the code for that. So we want to find a cycle. We will have 3 colors. So we will again use DFS of V. And then we color, like if color. So we have 3 colors, 0, 1, and 2. What does it mean? 0 means that we never visited this vertex before. 2 means that we visited this vertex and we already iterated its DFS out of that. That means that we kind of get out of this. And there is 1 that we got into the DFS but never finished yet. How is it possible? So at any moment the tree looks like that. So there are unvisited vertices, there are already visited vertices, and there are vertices that are like a path to some. So it's here it can be 0 and 0. Yeah. So it can be seen that ones are only for some path to some vertex, because like these are exactly the vertices that haven't finished their DFS yet. So you kind of in the recursion here. You kind of in recursion of this node, in recursion of this node, and in the recursion of this node. Then, if color v equals to 2, then we do nothing. We just return. If color v is equals to 1, then
well, it should be a loop. So
yeah, so it's exactly the cycle, right? So if this vertex has an edge to 1, then it is the cycle. So cycle here, cycle here. And then you can restore the cycle by going back from the recursion. So for example, here return false, here return, like I would say ans.add v and return true. Then otherwise the color of v is 0. Then we go to the DFS, so we set the color of v to 1 and go over all the neighbors for vu, e, and we say if DFS of u, this means that we run and it returned a cycle, we say ans.add u and return true. It will not be exact. I will say, and when we finish, we say that we finished the recursion here, so the color is 2. There is a little problem with that algorithm, which I'm not going to fix. Is that suppose we find a cycle here, right? The DFS will return the ans will be this vertex, this vertex, this vertex, and also this vertex, because when we return true, then we always come back. You should add an additional remark that if either you take the answer and remove everything that was before v, before the last in this answer, or something like that. That can be done. Do you understand?
Yes.
Okay, great.
I guess here we don't set the color to 2 if DFS of u is true.
Yeah, we just do nothing. We just return. So like each time when you have DFS u, you just return out of DFS at all.
Shouldn't we also set the color to 2?
Oh, why do we need? We stop, like kind of in this case we stop the DFS.
Oh, so
we kind of
one loop.
Yeah, find one cycle. Yeah. We wanted to find one cycle and exactly which vertices are in that cycle. Okay. This is about DFS and undirected graph. Okay. So there is an important. Okay, we're in the good time. There is only so we already know how to find the seg. That's good. So right now we will be talking about DAG and the top sort. So DAG is the dynamic acyclic graph that we already talked about. Like that. And we want the following. We want to set the numbers of the vertices in such a manner that there exists only one, like there exists only edge from the smaller to the largest. So in here it will be one. For example, this enumeration is incorrect because you have from 4 to 3 edge, which is from higher to lower. Instead of that, we have to do something like that. So in the question given their undirected graph, directed acyclic graph, to get this topological sort. What is the thing behind topological sort is that it kind of tells you the order in which you should do things. So you, for example, where you start from? You start from 1, then you continue with 2. You cannot go in 5 because 3 and 4 are yet not finished. So at first you should finish 3 and 4 and then go to 5. Then you finish 5 and then you finish 6. So this will give us kind of the very interesting graph where if we have it on a line, you will have only edges from left to the right. Only these edges. Because if you have from right to the left, then you either have then you have a cycle, or your topological sort is incorrect. So there is a simple way to do that. So we have our identifier to start with an n. And we go for UV in E, top sort V, oh, if, yeah, sorry, I need this. I still need this. And U, oh, was it V, then return. Then was of V equals to true. Then we go over all their edges from VU in E. We go top sort of U, and then we say that T of ID equals to V and ID minus minus. So the idea is that when we go over all the possible kind of how to understand that we got to vertex V and go and visit all the vertices that are reachable from V. Okay? This means that all the identifiers of that should be higher. Then we could simply say that the vertex V has the position, we can set V to ID. This ID because we already visited all the vertices in there which are reachable, and we already set them their new identifier. And outside, please don't forget that we have to go over all the vertices. We get top sort of I, because, for example, you can start top sort from. So if the enumeration was different and it was like 1, 2, 5, 3, 4, 6, then you start from 1, you visit 1 and 2, and you get out. Then you visit 3, then you visit 4, then you visit 5, then you visit 6. Because of the order of how we call them. So like from 1, the only reachable vertex is 2, so you kind of visited only 2 vertices in this case. And you set them the maximal identifier.
But the ID equals n is global.
What?
ID
It's global, yeah. It's global, yeah. Or you can use like kind of a vector where you put to the back and then you revert it. Or There is another way on how to do the top sort. Not recursively, this guy is recursively. Yeah, is it clear that its complexity is O of m?
of m?
Yeah, or the number of edges. Or n squared in the sense of adjacency matrix.
Okay, yes.
This. Okay, there is another way how to solve this problem. A very interesting way, however. So, which node could have their smallest identifier in a secret graph?
Well, in this graph, the topmost.
The topmost, yeah, but in general, can you identify these vertices? So, you have all the vertices, can you identify the one that will be with the smallest identifier?
Well, it should be a node which has all outcoming edges, I guess.
Yeah, so their in edge deck plus is equals to 0. So when you remove this edge, which vertices are next in there?
Also with the same condition.
Also with the same condition. So what we can do? We can have a queue, or like any other, but queue is simpler. So we have a queue where we put all the vertices with DAC plus equals to, if DAC plus V equals to 0, then add all these. Then, while Q not empty, we will do the following. We will just check, we just V equals Q dot remove. I already forget what is the right state. So this return the first element in the queue. And then you iterate over all the neighbors and reduce their degree by 1. And then if DAC plus U, then Q dot add U. Oh, sorry, equals to 0. So we just simply iterate over all. So we take the vertex and we iterate over all the edges, and kind of remove this vertex from the consideration. So this means that we remove in degree of each vertex, decrease by 1. And if it becomes 0, then it is our time to execute it, and then we can add it here. So why do you need top sort? For example, you want to find the longest path in directed acyclic graph. How would you do that?
Well, with top sort, it would be the one. So the first edge would be the topmost, and the number of the last would be the length of the graph. Well, so maximum number, or no, I guess not.
Yeah, it can be like that. We did top sort with some intuition that we needed. Like their idea of the top sort, you should think that their edges are going only to the right. So you have to find the longest path that is going to the right, kind of. That is like jumping by edges. So can you come up with algorithm that calculates their maximal path in this already strange conditions?
Well, I guess we could iterate through them and just find the maximum length, but maybe
How?
it should be faster.
How to
Well, if we do the DFS, for example, we can just go through it and store the maximum length that we achieved. But
you shouldn't think already as DFS here. You should think we already know how they're in top sort. You don't use top sort in your solution. You already run DFS and it's return their order in which element in which vertices are. Let me give you a hint. So, what is the longest distance from their node with 0 outgoing edges?
the longest distance to which?
To somewhere. It is 0, right? Because it has no outgoing edges, so it is 0. So we know for some vertices that there is 0. Then you go to another vertex, and it has some edge to 0. Then what will be its maximum number? It is 1, right? But suppose now we have another vertex and which has to some 1 and to some 0. Then what would be their maximal distance?
So it would be 2.
It would be 2, yeah. So it is by 1 higher than the maximum that we can visit. So
I'm sorry, by 1 higher than the maximum that we can visit?
process the statement and give up the solution, please. Any ideas? We solved this problem. There was a similar problem, but there was a grasshopper who jumped. So as you can see, this looks like jumps. Kind of.
Well, do you mean that when you say visit, do we start from the bottom? We start from the zero?
So you know, we already have top sort. You know that their edges are going only from left to right.
So zero.
So for example, the rightmost vertex, it will be 0 because like it has no outgoing edges. It has nowhere to go.
So if we go to maybe all of the vertices that go into this one. Well, with grasshopper, I guess we can store somewhere at the.
With grasshopper, we're starting from the leftmost and running to the rightmost.
And here we can go from right to the left and store the maximum number, which leads us to the 0, and then
exactly. Let me do this in a little bit simpler manner. Then you yes, of course you can go anyway. You go from the left to the right because you know that all the jumps are to the right only. And then you do the following. What you suggest, you want to go over reverse edges, the backwards edges. I will tell that it is not necessary. I just go for each vertex v from n minus for each I for n by n, then I get the vertex top sort of I, and then I go for each edge from vu. I say ans of v equals max of ans v and ans u plus 1. So we just go to each vertex and do make one jump. And the answer is the maximum where we can jump, plus 1, because this was the jump. Okay. The similar question, how to find the number of different paths.
Different paths to the...
In the dynamic acyclic graph, kind of the path is different. So for example, suppose we have an edge here. For example, this path, and I don't know, this path.
Well, so between two
very
vertices.
Different. Yeah, between some two vertices, but between two vertices there could be more than one path, because between this one and this one there is path like that, and there is path like that. You want to calculate.
And we should find the number of them, or all the paths themselves.
You want to find the number of them.
Also, we could do in the similar manner, just count the number of paths to get, well, the maximum.
Yeah, instead of maximum, we just can simply add some here and we will be done. Yeah. Good. Okay. So typically top sort, directed acyclic graphs are happening on factories or something like that, where you have the order in which you should make some result, and you have to pipeline in the right, you have to make them in the right order and not to forget about something. Okay, good. And let us talk a little bit about trees for a minute. So we know what tree is already. It is undirected acyclic graph. So, and we rooted by some vertex v. I mean, this root is where we kind of started the DFS. Okay. We will calculate so known as time in and time out. So the total time is here, time equals to 0. And then we go DFS of v if in of v not equals to 0, then return. Then we say t in of v is equals to time plus plus. Then we go for all the edges from vu in e. We say DFS of u, and then t out v time plus plus. So we store the time when we get to this vertex in the DFS and the time then we get out of this vertex in the DFS. So we calculate this t in and t out. The first question. The size of the subtree. How to calculate the size of the subtree? Tree of v. So we have v somewhere here. What is subtree? Oh yeah, let's do the t in and t out, of course. So we have 1 here, 2, 3. Then we go back. Oh, so it is 4 because we have no outgoing edges here, so we finish, so we have time 4. Then we go to 2, then we go to this vertex. This vertex becomes 5. Then we go here 6, you go out 7. Then you go here 8, you out 9. Then you have 10 here because it has no other edges here. Then we go up. 2 is already also finished, so we put 11 here. Then we go to 1. Then we go here, it is 12. Here is 13, 14, go back, 15, 16, go back, 17, 18, go back, 19 here because like we finished with 12, then we finish back, and here we put 20. So this is how we calculated t in and t out in this example. So can you tell me how to, given t in and t out, how to calculate the size of the subtree?
Well, I think it should be t out minus t in divided by 2.
Yeah, something like that, but if to be sure, like, can you calculate more precisely? T out. Like, I specifically did an example so that you can calculate.
Well, yes, we can either subtract 1 there or round it down, just so t out minus t in.
I would say otherwise. It should be plus 1 divided by 2. So you can check here. 10 minus 5. It is 5 plus 1 divided by 2 is 3. So 1, 2, and 3.
Oh, so including the...
Of course, this is the subtree. The subtree is a kind of connected graph.
Okay.
Yeah, so this is, right now we understand how to check for the size. Okay, good. Suppose we are given 2 vertices, u and v. How can we check that one is the parent of another? Okay, yeah.
Well, if some of them is if its interval between in and out is inside another one's interval in and out, then one is paired to another.
Exactly. So in this case, if one interval lies in another, then they're the parent. Okay. So now we will be talking about a very interesting problem named least common ancestor. So it also appears in biology because they phylogenetic trees. I think we already talked about them.
Not yet.
Not yet. So this is kind of how the species were created, and then you want to find their least common ancestor, kind of two subtrees. And this table is of course very large, and you want to do this quite fast. You want to calculate this quite fast. Okay, so we already know how to check whether one vertex is the parent of another. So this is the good start. For example, suppose that for each node we know its parent. So like we set. So for u, this one is the parent of u. Can we come up with the algorithm that works by the height of the tree? So we want to know for you are given two vertices, uv, and you want to calculate LCA of uv. Like the first stupid solution that comes to mind. Not very stupid. Which depends on the height of the tree. Let it be even better. So let's be this two. UV.
Well, if the height is just for some optimization, then we could take the. Do we know the T in and T out?
Yeah, you know, we pre-calculated it, so we know T and T out.
Okay, so we can take the minimum height of those two and
Know what to do next?
well, at first I guess we should check whether this one with the minimal height is the parent of another, and then we should go to its parent and check whether its parent is a parent of
Yeah, exactly. So you can, like, this doesn't matter whether you take the minimal height, you can start with V and like go like that, check. This guy is the parent of you, now. Then go up, is this guy's parent of you? Yes, then it is the lowest common ancestor. Oh, sorry, why least? Lowest. Sorry, lowest. Lowest common ancestor. Yeah, okay. So this is very interesting, but can we do it faster? The question is. What is their idea behind how to do this faster? We want this to do in logarithmic time, so we want kind of to jump faster. So here we jump only by 1, but what if we jump by 2 in the power of something in the first place? That is why we create an up table for each vertex u and the power k. This up uk is who is the parent of u if you have the jump of 2 in the power of k. So how to calculate this table? We just go, like, it's better even have to like this one. So can you tell me what is up 1u?
It's parent.
It's parent, it's simply parent. It's an parent of u. And then we go for k equals to 2 to log n. We say go for all the vertices. We say up k of u equals to what? Like we want to get 2 in the power of k minus 2 in the power of k. And how to calculate it? Using the previous. So let us take an example. Like we have the parent and we have the parent. Then when the k is 2, then who is the parent? Who is, like, it's parent of the parent.
I didn't get the last one.
So I mean, it was the distance 1, and then how to get distance 2? It is the parent of the parent. So
Well,
this
yes.
guy is the distance 2.
Yes.
Then how to get distance k if we know distance k minus 1?
Well, it should be the parent of the parent, but
Yeah,
the power.
Exactly. So it is up k minus 1 of p, or of up k minus 1 u. And that's it. So it's the parent of the parent. So it's the parent, like it's kind of like 2 in the power of k. It is 2 jumps by 2 in the power of k minus 1. Okay. We know now faster how to faster jump. Okay. Then how to find the LCA? In logarithmic time.
So, if we just iterate it through this up, this would be like binary search, I guess. But well, I mean, we should do some kind of binary search, right? Here, and if you want to do this, we just take the last, well, the last parent, the biggest 2 in the power of k jump. Then, if it is parent, then we take the jump of 2 in the power of k minus 1. And in the other case, we take the jump 2 in the power of k minus 1.
Exactly like that. So you k from logarithm n backwards to 1 if pk v is parent of u, then do nothing, otherwise jump pk v. And then the answer will be p of v. Because we always jump when we are not the parent. We always jump if we are not the parent, and then we will finish at the node that is 1 step lower than the lowest common ancestor. Get it?
Yeah, and what is the for k from
For k from logarithm n back to 1,
and n is
n is their number of vertices. This is exactly where we have here, like there, because in the worst case it will be a chain that 2 in the power of n, 2 in the power of k, we can have a jump where k is logarithm n.
But this wouldn't always be, so if we take logarithm n, some of the up nodes should not be filled, no?
No, we pre-calculate everything before. So there is a pre-calculation in of and logarithm and time. We do the pre-calculation, we calculate t in t out, we pre-calculate this up thing, and then we are asking for, like we several times ask for the lowest common ancestor.
I mean, so if you start at k equals 2 in the pre-calculation, and we go to logarithm n, so we have...
Oh, sorry, yeah, I think it is 0, and here is 1, yeah, thanks. Because we have 2 in the power of k, so like the parent when it is 0. 2 in the power of 0 is 1, yeah. Back to 0.
Okay.
Is it clear? Okay. So I think that's it for today then. Thanks for coming.